Okay, so just a note. I guess Thiago sent out that email. He didn't check with me to collect the homeworks that you guys turned in last Thursday. So don't be upset. Those of you who had turned it in, I have all those assignments, and I asked Thiago to check with me and to make sure he picks up the homeworks that were given to me before he sends out, alarming emails to everyone. So anyway, don't be concerned about that. If you turned it in, I have it, and we'll be passing it on to Thiago to grade. So today, what I want to do is to kind of do a bit of a review for the midterm on Thursday. And also, I think the homework 4, let's see, I said I think it's going to be due next Tuesday, but I don't think I'm going to be able to go over the rest of that material in time. So why don't we just keep an open date on that for now? It'll either be due on Thursday if I get through kind of going. I want to on Thursday on next Tuesday. I want to go over the midterm, and if we have time left after that, I'll continue going through some of the coherent stuff, and then there's not too much more to do, but there is some stuff on the laser modes, and then there's some stuff on visibility, I think, and exposure. So I want to give that information to you. So homework 4, it'll either be due the 29th or that Tuesday after, whatever that is, November something 3rd. Is that about right? So I will keep you posted on that. All right, so hopefully all of you have seen the midterm from last year. And so again, there's some constants here, and there's also some of these Bessel function values that, kind of do a quick check of what I give you on the front page, because that'll be an indication of maybe what to expect. So if I give you these Bessel function values, you know that you're going to have to do something with the phase grading, right? Because you got to calculate your JQs. Okay, so let's look at this. All right, so the first question here is we have a hologram recorded with 2 plane waves at plus and minus theta relative to the z-axis at a free space wavelength of 670 nanometers in a material with a maximum spatial frequency recording capability of 2,000 lines per millimeter, which is half micron resolution limit. It also has a refractive index of 1.5. And so the question is, what is the largest angle between the object and reference beams in air that can be recorded with these conditions? All right. So do you know how to do that? How would you do that?
We would start off actually at the interface and say, okay, our k vector is 2 pi over the maximum spacing that we've got.
Okay.
And then from there, try to work back.
Yeah, that's good. So look at some other information. So I say you have plus and minus theta, so you have an unslanted grading. So that means you don't have to really worry about the refractive index so much, because the grading is going to be, the fringes are going to be perpendicular to the surface like that, right? And so if that's the case, and again, you should think through this a little, just take a quick thought. See if you can get away just using the grading equation. Right? So the grade. So this again, this is just the. This is going to give you. This is the x component of the period. So this is going to give you the x component of the grading vector. But all I'm asking for are what's the maximum angle? So first off, these angles are this is a minus theta, and this is a plus theta. So this is going to be 2 sine theta equals lambda over the period. And so let's see, we had a wavelength of 0.67 and a period of 0.5. So that tells us, so now divide that by 2, and we end up with the angle. All right, so we have so if you divide it by 2, notice 2, that's 1. So it's pretty simple. Sine theta is equal to 0.67, and so theta is equal to 42.067 degrees. And if we want between the object and reference, it would be 82.13 degrees. So, I'm sorry, 84.13 degrees. All right. So again, just kind of a simple question, and asking you to, take advantage of, for instance, the unslanted grading here, where again the k vector is in the x direction, and we could then use simply the grading equation. Yes? I'm sorry, what? Yeah. So again, because so this is 1 and this is n, if this were a slanted grading, so what if we had one beam come in like this and one beam like that, then we would have to worry about the refractive index, because again the period, or the fringes lie along the bisector, and we need to, again, we would have to adjust this angle inside, follow Snell's law. So we have sine theta equals n sine theta prime. So this would, kind of rotate that fringe orientation a little bit. But here, because it's unslanted, the fringes form, again, along the bisector, and so the fringe angle is 0, okay? And so we don't have to worry about Snell's law in that case. All right. Good question, though. Okay, so when we have a tilted grading, a tilted slant of the k vector, we do have to worry about that refractive index and do the refraction at the interface. If we have unslanted, then there's not a problem. If you forget, and if you can go through it, right? But then remember, so if you refract the beam in, so you would have these angles, with n sine, sine theta over n inside the medium, and then you would also have a lambda over n, and then you can see that the n drops out from both sides. Okay, so if you forget, if you got that part about the unslanted, you can just kind of brute force it without too much extra effort and come up with the same result. Okay. All right. Okay. We good on that one? All right. Good. Okay. And then here, part B. Describe the steps involved for recording and reconstructing a holographic image. Show a sketch and the relevant equation for each step. Assume that the object wave is O, A0, e to the minus j phi, and the reference beam is R, A equals AR, e to the minus j phi r. Give the reconstruction conditions and expressions for the reconstruction of the original object wave and the conjugate object wave. It'd be easiest to describe the steps with simple sketches. All right, so again, this is just the holographic recording process. So this is A, and this is B. And so the first step, of course, is if here is R and O, we form a interference pattern. All right, and so we have I is equal to O plus R squared, and so this, we've written this, many times now. So I'm just trying to see if you remember it. And then we have R O star plus R star O. And again, so these are all complex, and we sub in the values that we have for O and R. So in that case, we have A0 squared plus AR squared. And then we have plus AOAR e to the j phi O minus phi R plus AOAR e to the minus j phi O minus phi R. Okay. All right, so that's the first step. And then the second step is we place some material there. So we have our fringes, and we put something there that's going to respond to those illumination patterns that we have, and that gives us a transmittance function which has some proportionality constant that again relates the intensity function that we have to that transmittance function. So this is actually this is the hologram in a sense, right? This is a thing that we end up with. And then for the reconstruction to produce the original wave, original O, in that case we would have, again, here's R and O. And so we would come in here with the original, with P equals R, right? And that would produce O, like so. And so in this case, the reconstruction field that we have is the original, P is equal to R times T, right? So that is to give us the original object field. And then for the conjugate object field, we have, so we want to get this term, all right? And so we would reconstruct that with P equal to R star, right? And so we would have W equals R star times T. And R star is, if this was our original field coming in, we want to have this back propagating wave is our conjugate, and that's going to produce O star like that. Okay? So again, just what we've talked about a number of times, but it's something I want you to take away from the class is understand what the process is for forming and reconstructing a hologram, both for the original object as well as for the conjugate of that object. Any questions on that? That one? Okay, good. All right. Moving along then. So the next question here is kind of a giveaway here. Draw an experimental setup required to record a transmission hologram as used in the lab experiments. All right, so we've done this a lot of times. Hopefully the distant learning students are not at too much of a disadvantage because I've gone through this in class. So even though you didn't do it with your hands, you should know what this looks like. So again, so we have a laser. The beam coming out of the laser is a nice pencil beam with maybe a diameter of a couple millimeters or a millimeter or so. Then we use a beam expander that consists of a microscope objective, focuses that light through a pinhole. So this acts as a spatial filter. Then the beam comes out of that, and then we collimate that. So we have a lens here that's a collimating lens. All right, and so then that beam goes out, and we have to divide it in some way. So we use a beam splitter. Allows the beam to propagate in two directions, so we have two different paths that we can manipulate, and we end up setting up really an interferometer, right? So this is a set of mirrors, so we have M1, M2, we have our beam splitter there, and here is where we would place the film. Okay, and then if we wanted to record some object, we could maybe have this illuminate a little object here, and the light would come out to form a kind of an image hologram of some sort of object. All right. So again, that's all. Just again, something you should know when you graduate from this class. Yeah.
So in this setup, I understand everything that's going on. What would you necessarily expect us to have as far as labeling? Because I see all the different components and understand that they're there. Do you need us to label M1, M2?
No. It might be. If you just show it's reflecting like that, I'll understand. Maybe this spatial filter and collimator, because that has some functionality, because we need to expand that beam really, right? So we're trying to get it. If you don't do that, it's going to be.
We've got the microscope projected and then the pinhole and then the lens. You can just say spatial filter.
Right. So for instance, if you left out the spatial filter, I'd probably ding you a quarter point or something like that. If you left out M1 and M2, I probably wouldn't do anything. It'd be good to put where the film is, and probably the beam splitter, so you kind of understand what's happening with that. But yeah, that's a good question. So that's about the level of complexity I would want you to put down on that. Again, you don't have too much time. You have to think through things quickly and hopefully understand it. So I'm really trying to test that you know the basic things. So I mean, you can get an idea here. I'm making sure that you know the grading equation and what that means. I'm making sure you know what the holographic process is. Making sure that you know how do you make a hologram. You need an interferometer in order to make the hologram. So that's kind of, you'll see here. I mean, there are some questions that maybe ask a little more detail, but they're more. I try to be a little more just conceptual on the exams and reserve the more detailed calculations for the homework sets, okay? Which, I think in an hour and 15 minutes, you can't, ask too much detail in a question. If I gave you an overnight exam or something, it'd be different. Take-home exam. Yeah, I used to hate those because they were always a magnitude more difficult. Okay, let's move on here then. All right, so this question has to do with coherence to some degree. Let's see, I'm not going to ask you anything on coherence on this midterm because, again, we didn't get that homework set in on time. But we know how to do this problem, so let's go through it. So here we have an optical source with Gaussian emission profile. So we talked about these different emission profiles. They have different bandwidths due to the broadening process in the medium. And so it has a nominal wavelength or average wavelength of 650, full width half maximum of 5 nanometers. Determine the maximum path length difference for a hologram setup that corresponds to the coherence time for this source. So here, so what that would involve, so a question I might have asked, maybe on the final now would be, how far apart can I separate one of these arms, or where, how much leeway do I have in the path length difference for these arms, which is what I'm asking in this question. So here, so we have a Gaussian profile with a lambda bar of 650 nanometers and a delta lambda of 5 nanometers. And so the Gaussian profile, remember we said that for that we end up with a coherence time which was 0.664. There was, square root of 2 ln 2 in there, 2 pi ln 2 and so forth. And so all that boiled down to 0.664. If you put that other value in, that's fine. You'll just have to calculate it. So we need the delta nu full width half maximum. So how do we get that? So you should know, I guess, that nu is equal to c over lambda, right? So if we take a delta nu, or a derivative of this, we end up with minus lambda to the minus 2 delta lambda c. Okay, and so for a 650 nanometer and speed of light and so forth, and the bandwidth of 5 nanometers, so we have 3 times 10 to the 8th meters per second over 0.65 times 10 to the minus 6 meters squared times 5 times 10 to the minus 9 meters for the delta lambda. So we end up with a delta nu here, which is 3.55 times 10 to the 12th hertz. And then, so that's the value that we need. And so we put that in there, and we end up with 1.87 times 10 to the minus 13 seconds. And the coherence length is c times that coherence time. And so that's about 56 microns. So not a very large coherence length for that source, but again, that's what you get when you have bandwidths of like 5 nanometers. Okay. All right. So so that's that. All right. The next. Any questions on that? Okay. What?
What part of the question is this?
That was question 1D. 1D. There we go. D, that's C. And now we're getting to question E. All right. Now, question E is there's a lot of, I have a graph, I have an equation, I have a lot of discussion, but the problem is actually pretty simple. So let's look at it. So here, again, is a material response to an exposure energy density that we have. So see, this is millijoules per centimeter squared, and this is the refractive index for like the phase material, which is our polymer bare material that we're using. So before we talked a little bit about, we talked about the Herter-Driffield curve, where you had density versus exposure. So this is a little bit different. Here we have refractive index versus exposure. But the idea here is the same. We have a curve which is nonlinear down here, and then it becomes linear in this region here, and then it saturates and again becomes a nonlinear curve out beyond a certain exposure range. So if you're making a good hologram, what you want to record is something that looks like this. So you want to record a kind of a linear response to the exposure to give you this kind of nice cosinusoidal function in the index modulation. All right. So here, so as I said, described that this looks similar to this optical density versus exposure. And now the question at the bottom. So here, so if the irradiance of the object and reference beams are each equal to 2 milliwatts per centimeter squared, determine the exposure time required for biasing the polymer for optimum linear response. Hint, what exposure gives the maximum linear response variation? Okay, so I won't put this point in here on if I gave you this, I put this point in afterwards. But you want to bias it like right in the middle of that linear range. I saw this really funny thing on, I I went, and if you ever go to Blue Willow Restaurant, they have a great little concession thing, or where you buy cards. So they had the thing on F's in exams, and so one on the cover of this thing there was a the what?
Talking about F's on exams.
Yeah, well, I thought it was appropriate, although not really. So the question was find X, and so they had a little, on this triangle, and this, I don't know, they gave 1 and 2 or something like this. And so somebody wrote, here it is. And they circled it. The question was find X, and so there's, I don't know, I just found that to be hilarious. Anyway, don't worry, no F's. You guys are graduate students. Okay, so anyway, so you want to bias this right in the middle of the of that response curve. So how do we do that? Well, again, this is just, like we kind of did in the labs or talked about in class when making exposures. So here we have the two exposure intensities, I1 equal to I2 equal to milliwatts per centimeter squared. So I average, right, when you do your recording, you have I1 plus I2, so this is first 4 milliwatts per centimeter squared. All right? So what we need to know is the exposure that, or I should have said exposure time, that gives maximum, that's what I was really after. So the exposure that gives you, the exposure energy density is about 12, 13, something like that, right, if you look here on this curve. And so with that, so we have an exposure of 13 millijoules per centimeter squared equals I average times tau, right? So here you can see that tau is just going to be equal to about 3.25 seconds. Okay, so just like you do when you make a holographic exposure, and oftentimes if you have a material, you'll do a characterization to come up with this nice curve that we have here for the material. Okay, yeah.
So in your hint, you asked for the exposure for the maximum linear response variation. What is the actual?
What does that mean?
Yeah, what does that mean?
So that means
Why
that the variation in exposure can go the largest extent about this value and still be in the linear region.
Okay.
When it starts to get up here, you're going to get some nonlinear terms. So you're going to get some higher order terms. And when it starts to go down here, you're also going to get some nonlinear terms.
Okay.
So it's just like, an op amp or something. When you're trying to make an analog amplifier out of it, you have a range you drive the voltage to that'll make it nonlinear, and you hear kind of crazy sounds if you're using it for audio amplification. So same idea here. You have a material that has a response. You need to bias it, and then you can modulate it in the linear range. Okay. Okay. That was question 1. Question 2. Okay, so we have this holographic lens that I like to show and use a lot. And so you want to compute the magnitude and direction of the grading vector at point B. Okay, so here's B. And so I already drew it in here, but we have, now we have a situation where it's not, it's not a unslanted grading, or it's a slanted grading, too many double negatives. But I let you assume that the refractive index is 1, so you don't have to worry. Everything is 1, so mysterious material with a refractive index of 1. So we're just going to worry about calculating the grading vector there without, worrying about Snell's law. Okay. If I did say this is 1, and then you would have to do that. Okay. Again, it's a little more calculation, but doesn't really tell. It doesn't tell me any more information about what you know. I know you know how to use Snell's law, so I can have you do that on the homework. But here in the test, I just want you to show me the grading vector. Yeah.
If we were to do that, it's Snell's law first, then figuring out the grading vector, K1 minus K2, correct?
Yeah.
Okay.
So again, so here we have, so if I did give 1 and n, so this is 30 degrees, and so you calculate what your new angle is on the inside for that. You have to calculate what this angle is here. This is 1/2 centimeter down and 5 centimeter over, so that tells us what this angle is coming in as well. And then you would have to refract that into the medium as well, and then do the calculation. So why don't we, we could do it, set it up, and then we could do it so that, we have a refractive index there as well if we need it. Okay, so 2a. So first off, we have, again, so we have this here, and this is 5 centimeters and 0.5. Oops. So that angle, theta 0, we just have tan theta 0 is equal to 0.5 over 5, 0.1. So theta 0, 5.71 degrees. Theta r, of course, is 30 degrees, all right? Like that, all right? So we have 30 and 5.71. And so now we have, we know what the wavelength is, I believe, here. Yeah, wavelength is 0.55 microns, all right? And we have that n equals 1, but we could change that if we need to. Okay, so here we then know that using the Bragg matching condition, K0 equals Kr minus K, or we can rearrange that so that K is equal to Kr minus Ko. Now the sign here is not really important. So you actually have two answers because it's not really unique in that sense. The K vector could point one direction or the other. The magnitude will be the same because it's based on the difference, but it doesn't matter if we had Ko minus Kr or Kr minus Ko, or but it'll be it'll give us the same value. So at any rate, we have K now is equal to 2 pi n over lambda 1, all right? So in this case, if n were, say a different value like 1.5, then that would automatically, this is the free space wavelength, that would adjust that free space wavelength for us, right? And then we have sine of theta r minus sine of theta o in the x direction, plus cosine theta r minus cosine theta o in the z direction. So here, this is where you would change the angles. If you wanted, you would change that to a theta prime, where this would be the inverse sine of sine theta over n, okay, for Snell's law, refraction. All right, so you'd have to put those in there, and you'd have this n being non-equal to 1. And that, I mean, it's not that hard, but that's how you would do it. It would involve doing these calculations for theta O and theta R in the medium. All right. Okay. All right, so that's the value, and then I end up getting for K, here I have 0.5995 in the x direction minus 0.12901 in the z direction, and you have to multiply this by 2 pi over lambda 1. So remember, you had to pay attention to the signs here too, okay? So this angle is, this 5.71 is actually a negative angle, right? because it's going, according to our convention, it's coming down like this, where this one is going up. So this one is a minus 5.71, and that's a plus 30 degrees. Okay, so you got to pay attention to that. And so the magnitude of K then is going to be, we square these two atom, take the square root, and so we end up with 2 pi over lambda 1, 0.61322. And if we multiply all that out, putting in 0.55 for the wavelength, I got 7.005 inverse microns. So those are usually the units because the wavelength is in microns. All right, so that's part of it. And then the other part is the angle. Again, that's the K vector angle relative to the z-axis. All right, and so we can get that simply by taking the arctan of x over z. So we have 0.5995 and over minus, so we end up with a minus sign out here, 0.12901. Okay, and that gives a minus 77.9 degrees. All right, so that means that I didn't really draw it right here, but the so the K vector can be either, so here's minus 77.9 degrees, or it could be 102.1 degrees, right? Sort of this same angle here, which is what, 12, roughly 12 degrees over, so, or plus 102.1 degrees. So either of those two angles are okay. All right. Okay, and then I.
Do you definitely want us to give you that angle, or is it enough just to give you that x?
Let's see, what did I ask for? I think I asked actually for the compute. I actually asked you to compute the magnitude and direction of the grading vector. So.
I don't know, I feel like direction for me, because you did it in the vector. I would have left it in the vector form.
Okay.
But you're saying you want the angle.
Well, since I asked specifically what is the magnitude, that's a vector, yeah, but what's the magnitude of that vector? What's the direction of that vector? You see, that's a little bit different. If I just asked for the grading vector, you're fine. But if I asked for the magnitude and the direction, then I'm asking you specifically how's that oriented, okay? But otherwise, if I just said the vector, then that would be fine, okay? Okay, and then I say, how does the magnitude of the grading vector at point B, which we just computed, compare to the magnitude of the grading vector at point A up here? And then I say, no need to calculate, just look at it and tell me the answer. All right, so what's the relationship here? Which grading vector has a bigger magnitude? B has, right? Because of the greater this inner beam angle, the finer the fringes. We have that inverse relation. So these are very coarse up here. These are very fine over here. And remember, the magnitude is inversely related to those fringes. Okay, so again, that's something I want you to kind of internalize in your thinking. All right? So that was again, just a concept, do you know what I'm talking about here? Some of the basics. All right, now, okay, using the grading vector found in part A, which we just found, at point B, what is the longest wavelength that can be Bragg matched to the grading at that location? Okay, so what am I talking about there? All right, so this is part B. So I have a grading vector. So how do I determine the longest wavelength? Yeah, so the longest wavelength that'll still be Bragg matched is the shortest vectors that will still satisfy that relationship, right? And, produce a k-vector closure or, a vector closure condition. So here is k1 and k2, the two vectors, and here's k. So k1 magnitude equal, k over 2. That will give you the longest wavelength, and so that wavelength that we would have, again, so this is equal to 2 pi over the wavelength and 2, wavelength 2 here. And so using this value here, or if we look at this, we can, come up with the period and not do the 2 pi calculations, because this then is equal to pi over the period, right? And so lambda 2 is about 1.8, 1.79 microns. Okay. So another little trick on an exam too is, if you can keep things in terms of 2 pi for a while and see if you need to multiply it out, it'll save you a multiplication step if you don't care to do that. Okay, so now we have another part of this problem. So I'm kind of cheating. I'm giving you 3 questions, but actually not, right? I'm giving you more than that. But I'm kind of grouping them into different kind of topics here. Okay, so let's look at this. So now consider point A on the hologram. The hologram is reconstructed with a plane wave at the same angle as the reference beam, 30 degrees, but at a wavelength of 560 nanometers. And 550 nanometers was used for construction. And so now compute the z position of the image for the -1 diffraction order using the direction cosine and ray tracing method. Okay, so I'm not asking you to use the paraxial image relationships, specifically asking you to use the ray tracing relationship. So we have to solve this using, oh, and by the way, so in parentheses here next to the problems are the number of points that the problems will be worth. So you can kind of get a sense of whether this is going to involve a little more calculation or not based on the number of points that I'm asking for. Okay, so let's look at this part C here. So we're going to reconstruct it at theta p equals 30 degrees. That's our reconstruction. And so now we need the direction cosine. So we have, okay, so first off, what am I after? All right. So I want to find where the image ray so this is the hologram plane here, and this is the image ray that I have out here. And so I want to find where it intersects this z-axis. All right. So let's see how we can get that. All right. All right. So here again. So we have L0 is equal to xh minus xo over O, and so what is O? O is the distance vector. So we have, and again, we have coordinates on the hologram itself, right? That we were looking at point B was a half a centimeter below the axis. So we have xh minus xo squared plus yh minus yo squared plus zh minus zo squared in general. So that gives us the distance of that object ray, all right? And the object ray actually went back to a point down here, I think, for that position B. And then for MO, we don't have to worry. MO is equal to 0. And NO, is equal to square root of 1 minus this. So this, by the way, works out to be 0.196. All right, so NO is 1 minus 0.1961 squared, and that gives me 0.9806. Okay, so for those direction cosines like that. All right, now we also need LR, MR, and NR. All right, so if we look at this, oh yeah, so we were looking at point A. That's 1 centimeter up here. That's why, okay, we're not, yeah. All right, so we're looking at this point here. So here the object ray is, remember the direction cosines, what we're talking about is the angle relative to the x-axis. That's our alpha value. So this is, should be alpha here, right? So alpha is this angle. This angle was 30, so that angle is 60, okay? So here, here we then have LR is cosine of 60, which is half. NR, correspondingly calculated like that, is 0.866, okay? And then we have LP, again with this 30-degree incident angle. LP is equal to 0.5 and NP is equal to 0.866. Now, one thing we have to do here as well is that we have a mu which is not equal to 1. We have a lambda 2 which is different from lambda 1. So this is 0.56, this is 0.55. So mu is 1.0182. All right, so we do have to worry about that. All right, so now we can solve this by looking at, again, so we get Li. Li here is equal to LP minus mu LO minus LR. And so we end up with Li, putting in our numbers, 0.19057, which means that Ni is, again, square root of 1 minus Li squared. And actually this, again, it's a radical, so we have plus and minus. And so this is equal to plus and minus 0.98167. So we have to choose, right, the right NI angle. And so that we're going to choose the negative one because that's the one that's going to lead back and give us an intersection. So why, so this is kind of going like the way we developed the ray trace relations before, because this angle now is gamma I, right? That's gamma I for the ray relative to the z-axis, and tangent of gamma I is what we want, because that, with a value of 1 here, is going to tell us what zi is going to be. So if we look at the tangent of that angle, that's equal to 1 over zi, okay? And so from this, we have that zi is equal to minus 5.151. That's why, again, we knew that the distance was going to be negative here, and so we choose this value for Ni. Okay. So that's what I was looking for there. Again, a question that kind of, I mean, there's some calculations there, of course, but again, the main point here is, how do I use these ray trace relationships for the hologram? What do they actually mean? Okay. So, again, I will give lots of partial credit if you kind of lay out the method of doing this pretty well. Like, you have definition of your direction cosines, this relationship, of course, and that, and maybe a diagram. and maybe you screw up your numbers, well, you'll get, most of the credit for that problem, okay?
How did you get your xn, xo, yn, z?
How did I get this? Okay, so I have I have an object point, which was so here's the object point, and this is located 5 centimeters away at 0. So XO is 0, and XH is 1.
Can I move your other diagram down? That's
Oh.
the hand-drawn one.
The what?
The hand-drawn one you do on the other page.
Yeah. So again, well, this diagram is showing the reconstruction more so than the formation here. This is telling us how to get. The question was, how do I get the direction cosines? Where do I get the coordinates from? So this is where you get the coordinates for that. And again, remember, if you have a beam coming from infinity, then you just take, like the cosine of that angle, right? Relative to, say, the z-axis is giving you a, or I'm sorry, to the x-axis is 60 degrees. So you get the direction cosine L sub r from cosine of 60.
So you're saying like xn is, you're saying xn is 0?
X and xr, you mean?
I guess I'm still confused.
Okay, so if I give you coordinates, okay, this is a way for you to calculate, again, what the direction cosines are. If I give you, if you have a beam coming from infinity and I give you an angle for that, you can get the direction cosines just from the angles for those plane waves coming from infinity. Okay?
But you have points, and then these xn and xos are from the points that were.
Yeah, so again, so XO was 0, XH was 1, and YH and YO were 0. ZH was 0, and ZO was 5.